Okay, why don't we begin right now? So this is our last Young Il Colloquium of this year. So I'm very excited to have Professor Hong Tran from University of Wisconsin-Madison. Uh, Professor Tran has received his PhD degree in University of California, Berkeley, back into 2012. And then he moved to the University of Chicago as a postdoc, named as Dixon instructor. And then he moved to University of Wisconsin-Madison as a faculty, 2015. He also has received lots of prestigious awards, including Vilas Investigator Award and then Cy Young Fellowship. And as you might know, Professor Tran is advisor of Young Kim, Professor Young Kim. So we had a great time yesterday and today. I'm very happy to have Professor Tran. So he's going to talk about some recent progresses on policy iterations for Hamilton-Jacobian equations. Please join me in welcoming Professor Tran.
Thank you for your very kind introduction. So first of all, I would like to thank Yinsu and Yonan for inviting me and giving me a great chance to visit POSTECH. This is my second time coming to South Korea. My first time was just two months ago to KAIST. And it's really great to see a lot of friends here, like Yonan, Yinsu, Donghyun, and Jinu and Bumjun, lots of friends, lots of connections, and yeah, I mean, he was my first PhD student, right, from POSTECH, and there was Jiung Zhang also from POSTECH.
Yeah, our alumni.
Yeah, so yeah, lots of connections. I really appreciate it. So I'll try to tell you some stories about policy iterations. From the theoretical perspective, and I will also tell you that there are a lot of things that are interesting and needs to be understood more. And this is actually my first time giving a talk on this. I'll tell you the story. So I will try first to make it sort of introductory, and I'll try to explain to you the basics of optimal control. Although that they might look simple, but already that there are a lot of challenges that to me still not very understood even up to this day. So let's start with motivations. So lots of words here, so I'll try to draw some picture. Basically, we are looking at a very basic optimal control problem. Let me explain the setting first. So you have the state or your positions of a particle or agent is recorded as x of s. It's a point in RD. S is a time, and you have that it's moved according to this ODE. X dot of s equals to f s x s alpha of s, and your starting point is x. So in this case, alpha is your control. Alpha is a mapping from 0t to a, which is a compact set. This my notation for a compact set in Rm that is measurable. So your alpha is only a measurable map. So for each given alpha, you consider this ODE. Okay, so let me draw a picture here that for example, you can think about yourself driving. So this is you start at a time t at a given space x, and you are driving forward to a terminal time t, right? So let's say at every given point here, you can choose your angle of driving and your velocity of driving. Let's say this is a cone of possible velocity and directions you can drive. So maybe at this point you can drive in this directions, and then the next point you also have this cone of possible velocity, and then you drive. So basically your driving is controlled by the OD x dot of t, s equals to f of s xs alpha s. So alpha is your control. This is your control. And alpha s belong to a set A, which is a compact set. Okay, so you're driving, or you are walking around. Here I choose my control to go this way, it goes this way, you go this way. So it's moving around, and it's gonna end at a terminal time t. So that is a control problem. And then classically, you would try to minimize an objective functions the objective function J here has two pieces. The first piece is called the running cost. Running cost you can consider is the energy you lose when you're walking around, or the cost of the gasoline of your car, right? So the running cost is integral from the starting time t to the terminal time t, capital T of this cost, which is also given to you. And then you also have to pay for something called terminal cost. Okay, terminal cost is that, for example, if you land at this point, x of t, then you pay for terminal cost plus q of xt. Okay. If your part is going in a different way, then if you're going further to the left, then maybe you pay a different terminal cost. It's like you are going from here to Seoul, right? You have many different choices, and you need to pay the terminal cost, like parking price of your ending location, right? If you stop there, you have to pay for the parking cost. And then the basic problem in optimal control theory is to minimize this cost functional. So it's a basic minimization problem. And this is phrased in a continuous setting. It can be also phrased in a discrete setting, right? You can do it time step. Every step you move, and then eventually you end up with your location, and you try to pay for the terminal cost. In some problems, you can just set the terminal cost to be 0 or constant. Or in some problems, the running cost can be 0, it depending on the problem. And in the simplest setting, I assume that F, the vector field, C and Q here are all Lipschitz in all slots. Because if the vector field is not Lipschitz, or if there's something here, then it can be problematic. There's still a lot of studies, right? So some of you here do a lot of gradient flows and a lot of really exciting study with all this ODE. So in this setting, I assume that F, CQ Lipschitz. So the well postness is okay. You can say that although alpha is only measurable, but we can still just write out the normal well postness theory. Okay. So so the question is to do this minimization problem. Very simple, and that is the starting point of optimal control theory. Now, so although it looks like that, but it's not that simple, right? So why is it not simple? Because your optimal control problem, if you assume that this minimization problem has a solution called alpha star, typically they call it optimal control. However, this alpha star might be only measurable. It can have jumps. There's something called bang control in the literature, because bang meaning that you have to decide between just two actions, right? Go left or go right. So your control can be just measurable. It can be highly discontinuous. So finding minimizer is very hard. It's not easy. But in principle, it's doable. There's Pontryagin maximum principle. There are tools in optimal control to do that. However, the next thing that is also a lot more problematic is that if you solve this problem, let's say at this given starting point, you do it at Tx, you can find the optimal control. Now you move to the next point. Let's say this is a new point, T tilde x tilde. You try to solve the optimal control. Then you have to solve it again. You have to do it again. So at every different point, you have to do a very costly optimal control problem. It's not cost efficient, right? Because every time you start a kind of an infinite dimensional optimization problem. Because alpha is just a measurable function, right? So it's highly expensive and highly dependent on the location you do optimal control. So the question is that, is there a way that we don't have to restart the process every single time you do it? Is there a way so that you can do it sort of like, more systematically, right? And the third thing, this is something that I have been thinking about. It's actually not easy to state this, but I'll try to explain. is that what happens if the control set is only partially observable? Okay. Yeah. So this is what I think you asked me. Is the slide updated? I updated it a little bit. Yeah, but okay, this is fine. Yeah. So let me explain to you what does it mean by the control set is only partially observable, and why I think this is important. So this is unbiased. Yeah, maybe it's good to keep this. Okay. So let me explain a situation where the control set is only partially observable. Okay, so let's assume that, okay, now let me draw the problem a bit differently. So let's say that you are here. This is your given point T and X, and you are constrained within this domain. Let's say this is your freeway. You need to drive your car from this point to the end point, to the ending time T. Okay. So first of all, let's say that you can drive your car, you can turn your wheel in a given angle with fixed velocity, right? So if you drive very naturally, then if you are somewhere here, then you can go left, go right, and go with maximum velocity that you can, right? You want, right? However, if you go to near the boundary, for example, if you at this point on the boundary, you cannot go left anymore, right? Because you are bound within this thing. This is something called state constraint problem. That your state always has to be constrained in this set. So then, if at this point, then your velocity is only within half of this code, not the full code anymore, right? So that is the first thing that can happen. And then the second thing that can happen is that when you are driving, even you are driving to work every day, your path can be different because of the obstacles, because all the cars that are appearing on the road. So for example, if you're here and then you're at this point and then suddenly there's some obstacle here, right? So there's some moving obstacle. If there's some obstacle here, then if you're at this point, you cannot go right anymore, right? So at this point, the point T and X, maybe you can only go in some directions like this. And same, right? If you go up here, if there can be some other obstacle here and here, then maybe you can only go straight, right? So this is a problem with going from a location to a destination and avoiding obstacle. So meaning that at each given point T and X, your available control set is only ATX that is dependent on time and location, and it's only a subset of A. Sometimes this set is known beforehand. Sometimes this set is only known when you get near to T and X. So this is a very challenging problem. To my knowledge, if you formulate the problem this way, it's not solved. This problem is not solved because it, right? I mean, I talked to you and has some examples with the robots avoiding obstacle, moving obstacle. So there's some algorithm, but the theory is far from complete. Yeah. So this is something that always in the back of my mind, and it's not easy. Okay. So today I'm gonna explain to you just a vanilla type problem. It's simple, and then okay. Yeah. So this is the idea by Bellman, Richard Bellman in 1950s. It was not fully rigorous for this problem, but it's interesting. The idea is that instead of considering, you can see that as I said, this optimal control problem is very complicated if you change the locations. So the idea then is instead of looking at the control problem, first you look at something called the value functions. So you let V star xt to be the cost it takes for you if you start from T and X. you take infimum among all possible controls. And it turns out that these value functions solve a Hamilton-Jacobi equation. I will explain why very briefly. And the idea is that once you have this value function solve a Hamilton-Jacobi equation, and the idea of Bellman at that time was that, hey, why don't you solve the PD first? Once you solve the PD, you come back and find the optimal control. So the idea is that, because this is too hard if you take the infimum among all very rough controls, right? Okay, so let me now explain to you how do we go from this value function to the PDE. So it's all done through the so-called dynamic programming principle. Dynamic programming principle simply says that if you are doing some optimization problem, you have to be optimal all the time. It can't be non-optimal. Okay, so let me explain that. Very quickly. So yeah, this is x, this is t. You start at this point xt, right? And your ending time is capital T. What it says is that if you want to find optimal, let's say this is an optimal strategy corresponding to the optimal part, then what it says is that if you go from here to here, then from here to here it has to be optimal, right? So what you have is you have simply v star px is equals to mean and our infimum is the same. Integral from, you only go for a short term t to t plus h of the cost function, c s x s alpha s d s plus v star of t plus h x of t plus h. So it's optimal, it has to be optimal forever. The proof is simple, right? So you go from this point, this is the point that you end. If the later part is not optimal, then you would just say, okay, maybe I have a part that is cheaper, right? Then why don't you just calibrate it to go to from here to here, so it's cheaper, right? So this part cannot be cheaper, meaning that this has to be optimal. So that's exactly the dynamic programming principle. Very simple. But the reason why dynamic programming principle that is useful is that you can see that, hey, here I can do it, that I can do dynamic programming principle for an infinitesimal amount of time, up to only t plus h, and then I can use just calculus rule here. This v star at this location minus v star at this location, I can just use chain rule to derive the PDE. Okay, so let me write the PD for you. Maybe only one-sided. This is purely heuristic, but let's say you see that I have this formula, right? So it's equal to minimum or infimum among all possible control, meaning that if I take any control, I have V star is less than equals to this, right? Because this is infimum among all control. So for any control, I have this inequality. And see, now I'm just moving everything to the right. I take v star t plus h, x t plus h minus v star t x t, and I use the first two terms
the optimal one because we have a finite propagation, right?
Right.
And sometimes if you still follow very inefficient policies, but later it could be zero everywhere else, so that this actually globally creates the local global minimum.
Yes. So I understand your point in two ways. So let me try to exactly discuss that in two ways. So first, indeed, if you only look at the problem only in a short amount of time, then you try to find the optimality, it can be wrong. It's exactly related to what I talked to Yenin yesterday, that if you only do it in a small window of time, but you forget about the global structure, then the local minimizer can be wrong, right? So indeed, that is a very important point, that not only, so this is a very implicit like DPP. So not only that you have to optimize locally, but you also have to make sure that this is kind of the correct cost function for time from t plus h to t. So this has to be also a minimum. And then
so you're adding up the other rest of them.
yes, exactly. Yes. So that is a very important point, because in fact there's some greedy algorithm that only care about short amount of time. Let's say if I'm driving, right, I see in front of me a bunch of cars, I'm just driving it that way, but then maybe I'm ending up with something that is sort of totally out of control, right? So this one itself is the local information is not enough, but there's a hidden global information here. Yes, that's very important. Yes.
I have a question.
Yes.
On the next slide.
Yes.
So since you write this H as a Hamiltonian, is there any way to build this equation in terms of Hamiltonian dynamics?
Yes.
Because I look, H seems like some sort of Legendre transformation.
Yes, sure. Exactly. It is. I'll explain. Yes.
So in the previous slide,
Mm-hmm.
so it is something like diagonal algorithm.
It's
Diagonal algorithm. What? So find the shortest best finding algorithm.
the Zisha. Zisha.
Yes.
Yes, this DPP is also coming from front propagation or from Zijkstra algorithm that you try to do scanning and you move up a little bit. This is exactly from the level set method. Yes. Okay. There are lots of connection here. It can come from the geometric optics level set method, or it also can come from Hamiltonian system. There's a lot of connection here. Okay, I'll try to come to all of them. But indeed, this, I'm writing it this way. So it's hidden both the Lagrangian formulations and the Hamiltonian ODEs. I'll try to come to that, but it's exactly that. Okay, and you see that this proof is a heuristic proof, right? I'm just having that this is correct for all possible alpha, and that's why I can take infimum. And it's only the proof of, this is just a proof of subsolution. It's an easier proof. The super solution is a bit harder. And you can see that the problem of viscosity solution is that this Hamilton-Jacobi equation is that it's a very nice equation, nicely formulated. However, that typically the solution is only Lipschitz, is not C1. So because we were talking about that, so let me give you a very quick example that is related to Zijkstra formulation and geometric optics. This is always the very first example that people would give in viscosity solution. You can see it everywhere. It's also in the very first pages of my book that you consider this is here. So this is geometric optics in an essence. It's a simplest model of geometric optics that, assuming the speed of light is 1, you are considering how much time does it take. You are in this domain. You are in this room. How much time does it take for the light to reach you? That is a basic question from geometric optics and Zijkstra formulations. So clearly that the speed of light is 1. So clearly that if you are here, right, it's just gonna take you this amount of time for the light to reach you. So the correct viscosity solution would be this one, right? Your function u of x should be 1 minus x. That is the correct viscosity solution, right? However, you already see that it's discontinuous, right? Sorry, it's not C1. The gradient is discontinuous. But however, you can see that this problem has many solutions, right? It can go down like this and go up like this, or it can go down all the way here and go up. So there are many solutions. That is only almost everywhere. Among them, you can only select one viscosity solution. Anyway, it's a deep thing, but I'll come to that later. Okay, so now let's explain. Yes, so this is related to what you asked, and then I'll write down the Hamiltonian formulation of that. Okay, so people were talking about doing optimal control, right? So what people do is that we first solve this Hamilton-Jacobi equation, assuming that everything is nice, everything is smooth. If you can solve it, then the next thing you do is you say, okay, then what is my optimal strategy, right? Optimal policy? Well, if you look at this minimization problem, you can see that your optimal policy is essentially exactly the arc-mean of this alpha txp is exactly arc-mean of this Hamiltonian. Okay. And then if you have alpha txp is the arc-mean of this Hamiltonian, assuming that it's nice, it's unique, it's Lipschitz, then I can have my optimal policy is alpha tx is alpha tx gradient of v, and that gives me totally the optimal policy. Okay, so let me write it down. Yeah, I want to write that because then I want to explain to you what is the Hamiltonian dynamics formulation. So I have h of txp is equals to infimum of I in I of ct xi plus f t xi dot p. You define alpha tx p to be arc-mean I of this, then you would have alpha star of tx would be alpha of tx gradient star of b star tx. This would give you the optimal policy. You know how to drive. If you can compute the gradient, then this is your optimal policy. Then you can just see that your part, your control part is simply was written earlier, right? You have x dot of s is f s x s alpha s, alpha star of s x s, and x t equals to x. Okay, so you can drive. So if you can compute this, then everything's done. Okay? Yeah, so that's the idea. Again, I'll keep this one. I'll go to your point on Hamiltonian dynamics later. Yeah, so however, life is not that simple, right? In that example and in general, the problem for Hamilton-Jacobi equation was that this gradient is not defined everywhere. Yeah, so if it's only Lipschitz, then what is the meaning of this, right? What happens if you are going through all these singularities? It's not clear. Yeah, that's kind of the description of basic optimal control theory. Okay, so now let me go to tell you the policy iterations framework, and this is the reason why I got into this. Was that, you know, of course, I work on Hamilton-Jacobi equation, so it's kind of in my blood. But actually, I didn't know policy iteration until a couple of years ago. So this is very interesting. Policy iteration, they say that it's kind of like an approximate dynamic programming in the sense that you do policy evaluations and then you iterate to do policy improvement. And each of the steps you improve to get better results. This is very important in reinforcement learning, right? I mean, this is the reason why Bato and Sutton got the Turing Award, right? For reinforcement learning, right? They have a very influential work. Was it last year or 2 years ago? Bato and Sutton. What they do is the following. This is not well posed, but basically what you want to do is that, so you look back at this equation. H is the infimal of this, right? This is a nonlinear equation. You don't want to solve it. What you do is that you want to start with the first guess. You just guess what is your best control. You solve the linear PD, and then you update your policy. That's what you do. Okay. So you start with a guess. Alpha 0 is a guess. Instead of solving a nonlinear equation, you just solve a linear equation. This is a basic transport equation, right? You know, a lot of you are familiar with that. So you solve a transport equation, and then you update alpha n plus 1 to be alpha tx greater than Vn. Because remember that our control is exactly admin of this, right? So it's natural to solve this, and then you have gradient of Vn to be kind of nearly gradient of V, let's say, right? So you update your control, the policy to be this, and then you reiterate it. However, this didn't work. I think around during the pandemic, 2020 or something, I was talking to Yuming Po Zhang on a different project. Yuming Po Zhang, student of Inwon Kim at UCLA, and he is now at Auburn. He is working with at that time he was working with Wenping Tang in IEOR at Columbia. So they were working on this problem, and they saw this framework, and this is ill-posed. It simply didn't work. People tried, it didn't work. The reason why it didn't work, I can explain it very roughly. I don't have time to go into regularity theory for transport equations. But roughly speaking, let's say that I look at this, right? To make this one well-defined, well, at least I need gradient to be defined, right? So if alpha n plus 1 is well-defined, then Vn has to be Lipschitz, right? So Vn has to be Lipschitz. I look back at this transport equation. Okay, again, I don't have time to write out the flow map, but you can simply assume that the regularity of Vn and the regularity of A alpha n has to be the same, roughly speaking. So see, if Vn has to be Lipschitz, then I also need alpha n to be Lipschitz. Okay, so look back at this formula. If alpha n has to be Lipschitz, then I need gradient of Vn minus 1 has to be Lipschitz. So meaning that Vn minus 1 has to be in C2. And if I keep reiterating this, then I would need that V0 has to be in Cn plus 1. And if I let n goes to infinity, then that means that I need V0 to be smooth, which is not true. So this is ill-posed. People have tried to do numerics and write down the framework. It just didn't work. And Yuming Po Zhang and Wenping Tang, we were talking about some different things, and then they asked me, like, is there a way to deal with this? And then that's why we started the project. Okay, so let me tell you what was done earlier. So the earlier literature, right? You can see Howard study policy iteration for Markov decision process. I think some of you here know that. And then for optimal control problem, people study some sort of specific setting for linear quadratic or explicitly solvable setting. There are a bunch of important works here by Kleiman, Abu Khalaf, Lewis, Rabbi Pasha, Vanu, Abu Khalid, Lewis, and Lee Sutton. So Sutton here is in the battle Sutton for the Turing Award. So they did study this, and they also study stochastic optimal control problem. However, as I said, there's no general result for the first order convex equation, and also no result for the non-convex case. So that's the starting of our work. Okay. Right, so now let me tell you the main result, two main results, and then I will tell you some ideas to do that. And along the way, I will explain to you why this is related to Hamiltonian dynamics. Okay. Okay, now it's get a little bit technical. But this is the starting point of our ideas that, you know, when Paul Zhang asked us about this kind of equation, that yeah, it's not well posed because this is a transport equation. But then if we think about in the literature, right, when people try to solve nonlinear equations or even write out the numerical scheme for solving this transport equation, what do we do? This is a basic thing that if you write down the discrete scheme, finite difference scheme to solve this transport equation, you need to make the scheme monotone. If the scheme is not monotone, we are doomed. It has to be monotone. And how to make it monotone? Well, you add viscosity. You add vanishing viscosity. Okay, so if you look at this equation, right, you see that, okay, I'm writing it in the simplest way that I can. So I'm only discretizing in space and not in time. So it's semi-discrete scheme, just to make it simple. So this term is fine. The second term is fine. The third term here, you see that I have that it's phi of x plus HEI minus phi of x minus HEI over 2H, right? So I have this, but I don't know the sign of F. The sign of F is just a Lipschitz vector field, right? So it's not monotone. So what we do is that we have to add this term to make the scheme monotone. Yeah, so this is very basic numerical analysis, right? Let me just write down, explain properly to you why. Yeah, so you consider T V H of n plus CT of x alpha n. This is okay, right? But you have V H n of x plus x EI minus VHN of x minus HEI over 2H times with FI. I'm writing it in terms of coordinates. So it's sum in I, repeated sum in I, alpha n. Okay, so if I add the artificial viscosity, this is VHN of x plus HEI plus VHN x minus HEI minus 2 VHN of x over h squared equal to 0. Okay, so VHN at xt is okay because there's this stuff, so it's monotone. In order to make the scheme monotone, I need to make it monotone at h plus HEI x minus HEI. Okay, so you can see that means that I have that requires me to have n is greater than equals to L infinity now of f over 2 or something, strictly greater than. Then you see that this term is bigger than this term, so it's monotone. So and this term is bigger than this term, so it's monotone. So this is the basic thing about monotone of the scheme. Does that make sense? Yeah. Yeah. So it's the actual fact that when we solve the problem using finite difference, we need to add this term. And we realize that by adding this term, we have some leeway, we have some room for the viscosity effects. The viscosity effect is going to smooth up the equation and that allows us to do the things. Yeah, so this is a theorem proving with Wan Ping Tang and Yuming Po Zhang. It was done a couple of years ago. This is a year that is published, so I forgot when it was done. But anyway, we can prove that by doing policy iteration for the convex setting is monotone. So the value function is monotone. And further that we can prove that it's converging exponentially in n. So by doing policy iteration, maybe you can stop at this 5 steps. When n is 5 or something, it stops. Okay, of course, there's a weakness here that that the conversion rate is exponential, but depending on 1/h, depending on the step size. So it's really bad if h is going to 0. But okay, I mean, it is what it is, right? Because it is expected that if h is equal to 0, then it's U-pose. What can we do? I mean, if this is independent of h, I would be very worried. Okay, so it's getting worse and worse when the viscosity is vanishing, but we can prove that yes, it's exponentially conversion. Okay, yeah, and the key point is that solving linear equation is also easier, right? So I will tell you later about the proof, but about a different setting. I'll explain to you the key idea, but also that if we do finite difference, we have this this equation, and we can also prove that as the step size h goes to 0, we have some conversion rate of square root of h, and we have also conversion of policy. It doesn't matter. What I think, to me, what is matter is that in practice, when we solve the problem, we have to discretize it or use this collocation points or whatever anyway. And in the approximation step, we do have conversion exponentially of the value function and of the policy. And what is important here is that you can see that once you can compute the solution, you know the optimal policy for all time and space locations, right? You don't have to solve the optimal control problem every different time. So this is kind of one shot, and it helps you to find the value function and the optimal control, optimal policy at the same time. Yeah, so that's why policy iteration is important, because because policy iteration helps you to compute both value function and nearly optimal policy. Okay? Yeah, so now let me explain to you. Now it's more technical. But yeah, eventually I'll get to the point that is the idea is simple. I think I have to speed up a bit. Okay, so this is the so-called Hamilton-Jacobi-Bellman equation. I have viscosity here, but the Hamiltonian is non-convex. It's a sub-inf, so this is kind of two-player zero-sum game. The player A is trying to minimize your cost function, and your player B is trying to maximize the function. So it's a zero-sum game. One is trying to, get everything that he can, and the other one is trying to, like lose the least that he can. Okay. So this is complicated because for optimal control, there's only one player trying to optimize the value. But here it's a dynamic between two players. Okay, so we assume that there's admin and admax. That is okay. Now it's a bit more complicated. Yeah, please ignore this with me. This is not important. This can be costly, but we can compute it beforehand. Basically, policy iteration is, again, you start with two possible policy and you solve this linear equation. L is given to be just this one, right? So it's a linear equation. This is not too important. If you write down, you're going to see it's exactly that. And then after every step, we need to update the policy for both players, A and B, to be optimal. And then we plug back and solve the equation again. Okay. So this is the result with Xiaoqin Guo, my former postdoc, who is at Cincinnati now, and Yuming Po Zhang at Auburn, that we proved that indeed for this policy iteration, we also, for the non-convex viscous case, we also have conversion rate exponential. So earlier we did it in the first paper, we did it in the L2 norms. Okay, Jonathan told me that for him L2 norm is more important. So in this case, we spice it up, and then we found out that we can also prove the conversion in L infinity norm. Okay, so I will explain to you the idea of this result. It should be interesting and simple. Okay, all right. Before that, yeah. So there's really an exciting set of developments. So there are a lot of Kims here, so I have to write down their first name. So by Lee and Yenin here, study policy iteration via deep operator learning for Hamilton-Jacobi equations, and Yang and Kim and Yenin Kim. I was told that Kim is also Kim, right? Okay, I just learned it today. The pin-based PI and Young Jung Kim, Yenin Kim, and Min Seok Kim and Cho study pin PI for stochastic optimal control, and then Huang Wang and Joe for entropy regularized stochastic control problem, and also Yeon Jung Kim, Cho and Min Seok Kim and Yenin Kim, pin PI for exploratory Hamilton-Jacobi equation. This is very interesting, but I don't have time to get into this today. And also for epidemic models that Min Seok Kim, Yeon Jung Kim, and Yenin Kim study that. This is very important. I'll come back to that by the end. Hopefully I have time to explain a little bit. But before that, let me tell you roughly one idea, right? I mean, in one math talk, you should see one idea. So the idea is very simple. How do we prove something decay exponentially? It's just this very simple idea. Of course, in the paper, it's not written this way, right? But eventually, we make it very simple like this, that let's say you want to prove AN decays exponentially, okay? So an idea is that we would try to find a non-negative sequence Bn so that we have this inequality, okay? Why? Because you can see that because AN is non-negative, you automatically have that 2Bn is less than or equals to Bn minus 1. So Bn is already decaying exponentially, okay? And then you look back at this inequality, you say, oh, but then because Bn is also non-negative, so I should have An is less than or equals to Bn minus 1. And Bn minus 1 is decaying exponentially, so we get An decay exponentially. So that's the idea. We're gonna find an iterative An and Bn to satisfy this simple scheme. Of course, this is ad hoc. I mean, we did it first, and then we found out that it can be interpreted this way. Okay. Yeah. So now let me explain to you how do we put things together. The idea is very simple. The idea is basically a basic problem in Evans' PDF book, or a basic problem in Gilbert-Schrödinger. The idea is this: if a function is harmonic, then if U is harmonic, then U squared is subharmonic. Okay. So if I have U satisfying this linear parabolic equation with the right-hand side, I'm gonna take its square. The moment I squares it or I do some convex combinations, I'm gonna have some good thing coming out. Okay, so why? Because if you compute it, I compute LU square. I have U square T I X Laplacian of U square, and this is the basic thing that we often ask our students to compute in vector calculus problem, right? And this is also coming up a lot in all this problem from well, this is called the Bernstein trick, but also coming up a lot in geometric analysis and others. That Laplacian of U square is equals to 2U Laplacian of U. This cancel out, but I have this good term, the U square. So this good term is good for me because I can use it to play a lot of games.
What is the title? So you said it's a Bernstein type method.
Yeah, Bernstein type method. Yeah. Yeah. This is the first thing that I mean that we need to learn from Craig Evans. That if U is harmonic, then U squared is subharmonic. That's the first thing. And of course, again, it appears in a lot of like Li Yao type estimates, right? Or
say cheese derivative.
Yes. Yeah. So it's very simple but very effective. Yeah. So I'm gonna need this non-negative term. Okay. So So let's okay. I'm hiding a lot of things, but let me try to explain to you how did we do things, right? So to prove exponential decay, we look at the difference of Vn to the actual solution. We subtract it. We're gonna have. Let me recall the equation here very quickly. So you can see that I have this linear equation, right? And then V satisfying this Hamilton-Jacobi equation, but I'm going to treat the Hamiltonian or the Lagrangian here as just error terms. So I'm gonna just put everything to the right hand side. So what I see is that I have the difference solving a heat equation with some error terms. Everything error terms is the Hamiltonian minus this policy evaluation. I just push everything to the right hand side. This is a bad way, but we don't know a better way at this moment. And then we consider the difference of the Hamiltonian and the Lagrangian here. The difference, I mean, it's provable that it's kind of Lipschitz. So in squared is less than or equals to constant times dun squared plus dun minus 1 squared. Okay. So if I'm only looking at un, I don't have any tool. I don't have anything to do. But the idea is that if I look at un square, I start to have some leverage. I start to have some term to play with, right? I have 2c times dun square here. And this is good because I can use this to bound the bad terms here. So I'm just using the basic Cauchy-Schwarz inequality because un times in is less than or equals to this, the first two terms here, right? And the second terms here can be absorbed by this term in part, not all, but in part, because I still have dun minus 1, but at least I have this inequality. But you see, this is C over 2, right? So it start giving me the iteration process. I have this inequality here. And now if I define Cn solving this equation with the right-hand side, I treat this one as the right-hand side, and I'm starting to have, combining things together. I start to have L of e to the ct un squared plus 2cn minus cn minus 1 is greater or equal to 0. So you see that, let me recall here that in order to do this iteration process, we need 2bn minus bn minus 1, right? So if I do that, you see that I have, this is like 2bn minus bn minus 1, right? We designed it this way, with Xiaojin Guo and Yuming Tozan. So we designed this way that we have this iterative inequality by maximum principle, and with this iterative inequality, we can bound that e to the ct un squared is decayed exponentially. Okay, so that's of course, again, lots of technicalities are hidden, but the key idea is that is from the Bernstein method. Is that if we square it, we have a good terms to dominate the bad terms, and then we iterate it. Okay. Yeah. Okay. So now let me make some concluding remarks and relate it now to Hamiltonian dynamics. So let me say Hamiltonian dynamics first, and then I will go to the concluding remarks. So indeed, I have this Hamilton-Jacobi equation ut plus h of tx du equal to 0 in Rn cross 0 to t, and this is a terminal value problem. I have ut xt equals to q of x on Rn. Okay, so this is one way to look at the optimal control framework. I can look at the Hamiltonian system framework. So if I solve this Hamilton-Jacobi equation, assuming that it's solvable, right? Then in fact, my optimal control piece is nothing but I can find that the velocity v okay, let's see how do I write down. I can see that the optimal part, let's say let's go with x star t, gonna satisfy instead of this inequality, in fact, I have x dot of s equals to dph of x of s xs d v star, the solution of s xs. So it satisfies this one. This is exactly the velocity coming from Fokker-Planck type equation, and this is exactly going to give you the Hamiltonian system. So let me write down a little bit more. So, in Hamiltonian dynamics, you would define P of S to be the gradient, dV star of XSS. Then you would get, so this gives us the Hamiltonian systems that XS PS. So I have XS, X dot S equals dP S XS PS, and P dot of S, if you compute, is minus dx H of S XS PS. So that is exactly the Hamiltonian systems. So you can see that in this one, I wrote it to be F because it's just coming from the optimal control framework, but hidden here is exactly the Hamiltonian systems that we can also use.
Thank you.
Yeah, so it's actually very interesting. Okay, yeah. I updated this slide a little bit, but I forgot I said that it's a same. But okay, so the question is that for now we have not used more property of the Hamiltonian. We really treat it as a perturbative term. We just throw everything to the right hand side and treat it. Do we have a better way to do it? And also that in practice there are a lot of discrete problems that are important, right? Is it applicable here? But the two last points I want to explain a bit more is we care a lot about the cursor dimensionality. Right? You can see that our work here is mostly theoretical. Let me explain very briefly. Let me just go very quickly back to the very first result. That if we do this approximations, this is finite difference, right? So let's say that if I have n grid points, if I have, what's my notations? If I have the number of grid points is 1 over h to the power n, right? If the dimension is 10, 20, or 30, then this is not solvable. In fact, the finite difference for finite elements classically only works in 3D at most. 4D start falling apart. It doesn't work. So although this is great, but our works are pretty much theoretical. It doesn't have the implication effect in practice, right? So the work of Yernan and others here, a lot of work that people are trying to overcome the cursor dimensionality, in the sense that people would consider collocation points. I mean, I have to learn a lot from Yernan, a collocation point. That instead of consider the for example, if you want to solve this PDE, where is it? If you want to solve this PDE, in higher dimensions, we cannot discretize it in a normal way by finite difference finite element. What you do is that you would consider some loss functions, and in higher dimensions, you would just throw a random samplings of points, right? We talked about this today. That even in 10 or 20 dimensions, you would just consider like 1,000 random points to do collocation points. And then when you do collocation points, you consider loss function, and you would do gradient descent to find possible minimizers. And this is also Google DeepMinds and other teams are doing this sort of collocation points using this a lot these days, right? So at the end of the day, you can overcome the curse of dimensionality, and it works for a lot of beautiful examples in multi-dimensions, in higher dimensions. So to me, as a theoretical PD person, I would like also to understand if you do random sampling, consider collocation points and auto differentiation, right? Because the point is that you do auto differentiations, you have the gradient and the Laplacian computed through the neural networks. Do you have some rigorous conversion rate for these collocation points using this? Let's say you throw out 1,000 points. Do you know how close you are to the actual functions in a more universal sense? Because they ran a lot of examples, a lot of cases. It works, right? But I want to see behind that is some framework. And then the next thing to me is the partially observable control set. This is a big business. Why? Because if you only see partially observable sets, you actually don't have the Hamilton-Jacobi equations. Every time you're driving, your optimal path is different. So think about, automatic taxi, right, and others, right? Roughly speaking, you know what is the optimal path, but if something happens, you would need to drive differently. So in other words, it's not that you know all the policy, all the strategy. Every day is going to be a different day. How do you do that? I don't think that in terms of theoretical framework, there's a theoretical framework readily available. Of course, in practice, people did that a lot anyway, right? So I don't know. So let me end it here. Thank you.
Okay, any questions?
In your Hamilton-Jacobi Bellman system, I see that the coefficient AX has to have a lower bound to proceed with those kind of the coercivity.
Yes.
Yeah. So is there any way that we have some clue from the discrete version to connect those Hamilton-Jacobi Bellman to the actual terminal problem, the Hamilton-Jacobi equation? Because in the discrete version, that's before we take the diffusion limit, but there is a vector h, and you have some estimate like bound by square root of h.
Yes.
So somehow, like if we can you have some estimate on c, and you send the lower bound c goes to 0.
Yes. Yes. So we did have those results in our paper. I don't have time to say, but okay. Yes. Let me say this is actually an important problem, and if 0 is still open. So there are some important books. Okay, it's a good point to mention. Right. So in fact, you're right. I mean, I actually care a lot about the possibly degenerate, right? Viscous HJB, right? So in practice, I only have A is non-negative, and it can degenerate somewhere. And the actual equation would be that I only have, that one, right? So Vt plus H of Tx V equals to A Laplacian of V. And again, this is only greater or equal to 0, and I have the terminal time. Yeah, so in practice, we also need to do, in the paper, what we wrote is quite messy because it's finite difference. And we do for both space and time. So it looks very messy, but let me try to write in this way. Vh of t plus h of tx gradient in h of vh equals to a plus some h to some power. It can be any power. Laplacian in h of v. H. Okay, so we did write this in the paper, and then we did consider this. Yeah, so in this case, we do have that VH minus V in L infinity is less than or equal to C times epsilon to the 1/8. Some power H to the 1/8. But this is not optimal. And there's some work by Krylov and by Hongji Dong, Krylov. also study this kind of balancing viscosity process, NH. But no result is optimal. So I talked to Sigurd Angernen, and Sigurd told me it's clearly not optimal. And the reason why is very simple. The reason is that when we try to approximate the gradient of V by the finite difference, if you do Taylor expansion, this minuses is going to be less than or equal to constant times the Hessian of V by Taylor expansion. So the difference between Laplacian of V and the discrete Laplacian of V, for a smooth function, Laplacian of phi minus the discrete Laplacian of phi is going to be greater than or equals to, okay, if I'm not mistaken, x squared times d to the fourth by Taylor expansion. So in order to control this process well, you would need to go to the fourth order derivatives. It's very bad. So that's why we have to do a lot of approximation. It's very messy. Then we get h to the 1/8, but this is nowhere optimal. In fact, theoretically, this is still a big open question that what is the optimal conversion rate and what can be known. We try really hard. We will come back, but I mean the reason is very simple. When you do Taylor expansions, suddenly you get to higher orders. And by seeing this, I appreciate a lot more the works of finite difference and finite elements from applied mathematicians because it's not that easy. The moment when you do approximation, and this exactly comes to the point that I was mentioning, that if you do collocations point and if you approximate your function by the function in the neural networks, you do auto differentiations, yeah, all these things is coming back. All these differences, right? Yeah, it's also related to the point we talked about yesterday when they do the Google DeepMind STEAM, right? Try to do that, then how to estimate the errors. Yeah.
Any other questions?
Yes.
For the differential game setting, given that the optimal policy is unique, do you have any quantification on the convergence of the optimal policy? Actually, there's a behind story about this question. One time I talked with a financial engineering guy, and he said, in that field, not only getting a optimal value, it is also more important to get the quantification of the optimal control, as rule maker really does care about the stability of the policy. So
Right.
I wanted to ask that question.
It's not stable. Yeah. So thank you for that. I also hide that point. That so in this case, when we do this policy iterations, we do have alpha n and beta n converge. Assuming everything is Lipschitz here, it does converge exponentially to alpha and beta h, depending on the step size. But when we let the step size go to 0, then it's totally chaotic, meaning that we only have conversion of subsequence.
Even if L has nice minimax structure.
Yes. Yes. So yeah. So the point is that we do have exactly that alpha n and h converge exponentially to alpha h, and also beta and h, assuming that everything is Lipschitz, and it does converge to beta h. But then the alpha h and beta h, as h goes to 0, yeah, this is a problem because of all this very unstable structure. In the control setting, then we can prove that we have conversion. But in the game, then we only have it up to the discrete level. And I think it would be wrong if we have conversion to the continuous level, because it just doesn't work. It's unstable. So meaning that, yes, you can solve it here at a given point, and you can say it's nice, right? And then here it's nice in the discrete level.
Actually, that's a pretty important problem in financial field. Let's say I'm a financial advisor and tell my customer to, hey, buy this stock and this stock, either guarantee the optimal outcome. And next day, I advise the different customer with different portfolio, but still guaranteeing the same optimal value, which is very weird.
Yeah, because okay. Okay. how do I explain this? Because it's a game, right? It's a game, meaning that, you know, yeah, so there's a game theory formulations, and in the game theory formulations that is really depending on the actions of this player, then this player is gonna play differently. So it's really dependent on both of the players. Not when you do the optimization for only one player, for optimal control is easy because you are the one that optimize it, but the other one is the game, and the game that there's the strategies. So in game theory, there's always hidden strategies that sometimes that people didn't take that into account. Because let's say two players are playing chess, or you are playing chess with a computer, right? What does it do? I was telling Yenin too, like if you play chess, if you or Go, right? If you make 10 moves, the computer gonna scan all possible strategies that it has learned. It thinks of 10 moves as kind of one strategy, one input, right? And it's gonna play the best strategy for these 10 moves. But then let's say in the move 11, you suddenly move in a very weird way. Right, and then it's gonna scan back the database and say, okay, this is totally different ball game. It's gonna play totally differently now. So yeah, this is why one day to the next day can be totally different because of this game structure. This is something that fascinates me, but it's very hard, I must say. That's the reason why it's unstable, right? Because what if you make a very genius move, right? It suddenly changes the whole game, right? You know, yeah. So that's why to me differential game is very hard. It's sort of
Okay, my very simple question is for the partial observable problem. Let's imagine the fixed, say, a fixed obstacle is located in the middle of the whole space-time domain. So how do we formulate problem? I mean, do we have to just confine the domain without the object, or do we have to adopt a kind of infinite wall, or do we have to do some impose some boundary condition on the object?
Yes. Okay. Thank you. Yeah. So that is a great point. So yeah, let me go here. Okay. Now there are different ways to formulate this. So let me maybe tell you two ways to formulate this. Of course all this problem you can think about the problem in the discrete setting. Let's say space and time or discretized is not an issue. So one way you can ask Janet, he has some movies about this, is that this is a state domain omega, and let's say that you're moving here, right? This is your car moving here. There's some dimensions to the problem, and you can simulate the problem saying that you have certain number of objects that are moving with certain trajectory. So this is one of the problems that assuming that you already know that there's some object in the domain moving with certain velocities, and then now you have to drive it so that you avoid the obstacle, right? For example, if you drive it up here, you see this obstacle, maybe you have to go here and whatever, go here. So there's one way that I asked him yesterday that how people did it is that what is it called? Is it window optimizations? The thing you said yesterday that people only optimize up to 5 time steps.
Model predictive control, MPC.
Model
Predictive.
predictive control. So far, this is what people do. So it's also related to Shinu's point from the beginning is that you actually don't try to do optimal control for the whole time. You could go like maybe 5 time steps. If you see some of the obstacle, then you try to be greedy. Okay, I see 5 time step ahead. I see some obstacle. I'm just trying to avoid them. And then next, I'm scanning the next time step. I keep scanning. So that is kind of greedy algorithm, right? It's not optimal, but it works, right? Because sometimes it works. Yeah. So that's one way to model it. So the one way to model it is that you would put in the system a number of obstacles, and you view this one as something called state constraint problem that you really try not to run into obstacle. So, but then you can say that this is not general, right? Because what if I have more cars coming into the road and other things, right? So that's one way. The other way that I have been thinking about is a little bit different. Is more related to what you say, is that maybe that one day I'm driving, I see no car, so that gives me one strategy. The next day I'm driving with my old strategy. So this is the end plus one, end day, right? So it gives me some prediction for the n plus 1 day. What do? I go with my strategy the previous day. I go, if at this point, if I see some cars ahead, then I update my control set. My control set, maybe now I'm moving it this way. So the control set A of xt, tx is updated based upon what I see, right? So you have to move here, and then if I see this obstacle here, then maybe I'm moving back here. But how do you formulate this? I don't know. Because you need to formulate it in such a way that it's solvable, right? It's tractable. If you make it too complicated, I don't know. But I would think about is related to policy iteration, is that the first time I'm driving, I'm in experience, I learn something, I learn more, and then I'm using what I know. And then if I see obstacle, then it's change the ball game, right? So I have to change it correspondingly. Yeah, so that's the second way. I view it as sort of like more up to date, right? I only see my control set maybe 2 seconds before, right? So how do you define it? It's hard. I don't have yet a very clean way to define it.
So people just understand this problem as in terms of algorithm.
Yes.
Okay, nice.
Yeah, and for us, we only do A is just A for all X and T. So for us, we study the toy model, right? But in practice, I would imagine that all this, reinforcement learning and all these things are done by a lot of statistics, a lot of data, a lot of things, and then you have to update it every time you do it again. I don't know how to do it mathematically yet. Yeah, but I think this one is more tractable. This one is a lot more hand wavy, right? Yeah.
Good. Anyone has further questions? Okay, otherwise, yeah, let's thank the speaker again. Interest in Young Il Colloquium for this year. See you next year.